Hello. I did it one more time. There's a 3. I gotta check that before I start recording. Anyway, we're doing 7-3 logarithmic functions. In earlier videos and in class, we'll talk about how scientists use logarithms to basically kind of like just make it easier. And you're probably wondering, well, how could this possibly make it easier? The logarithm is the exponent. So when numbers get really kind of extreme, I suppose, when numbers are very, 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 very big, like if we're dealing with astronomy and distances, or if we're dealing with like the Richter scale with magnitude of earthquakes, that scale acts really like it blows up a lot. And sometimes it's easier to understand it if we think about things in terms of magnitude. And the chosen route that we use is with the exponent of whatever base that we want to pick, usually base 10, that gives us that. So that's why we make what we call like a logarithmic scale. And that kind of doesn't make sense hearing myself say that. So I'm going to give you this example using pH, which is a way of measuring the acidity or how basic a solution is. I know some of you have been in chemistry, some of you had chemistry already, and some of you are taking chemistry next year. So I don't really know if I want to get into like all of the details with this. Hold on to this for just a second. I'm going to come back. But let me try to explain what's going on. And this is a math teacher explaining science, so please just Google this stuff, right? Okay, we all know that, and I'm not going to be very long with this, okay? So I'm not teaching an entire section of acids and bases in this. This is just like the bare bones of it. Okay, so we know that water, just pure water, has a chemical formula of H2O, and you've heard that, H2O. What does that actually mean? Well, without getting into like covalent bonds and all that stuff, electron shells, basically that means that you have one atom of oxygen bonded through shared electrons with 2 atoms of hydrogen. So I didn't draw big enough to put the H inside of it, but it kind of looks like Mickey Mouse, I know. So you got 2 atoms of hydrogen bonded with 1 atom of oxygen. Okay, that step you probably know from 7th or 8th grade science. You've gotten that far. But here's something that I don't know if you actually talk about. When you have just like a beaker of water or water in general, sometimes that hydrogen atom leaves its electron because they share an electron. Do I really want to get into that? In order for things to bond, you have to have filled electron shells. Look it up, okay? Sometimes this hydrogen atom will leave its electron, and instead of having a bunch of these things, you actually have this. So this is oxygen, this is hydrogen, and it's got a negative, it looks like a snowman now, I know. And it's got like a negative charge because it has an extra electron. And then over here, you have basically a proton. And that's hydrogen with a positive charge, with no negative charge. And yeah, that's basically a proton. Now, if you have a bunch of these and more than these, so that like in water, just pure water, those things are balanced, even if they're separated. At least that's the way that I was told, right? If you have a solution of something to where you have a bunch of these, an excess of these, more of these you have an acid. And if you have, for example, and gotta remember if I'm saying this right. So if you have HCl, which is hydrochloric acid, very, very strong acid, okay? If you put this into a solution of water, this is going to split easily, and you're going to get hydrogen ions, protons, and of course negative chlorine ions. All right, That's not that bad, but those are bad, okay? And they're not bad because they're evil or anything. It's just they're dangerous because they're highly reactive, and they like to react with things like human skin. So, oh, sorry, before I do this, this other one, this OH negative, if you have an excess of that, you have a base. Okay, I know I'm leaving out a lot of details. I'm probably oversimplifying it, and I know that because my job is not to teach the chemistry. In a solution, you might have more hydrogen ions, or you might have more hydroxide ions. At least I believe it's called hydroxide. What's the highest percentage of hydrogen ions that you could have? You could have 100%. 100% as a number is just the number 1. So if you have 100% hydrogen ions, then you have 1 full unit of hydrogen ions, nothing else. That's probably never going to happen, but it's a good place to start. Now we can go through like 90%, 80%, so forth and so on, but to be honest, we don't really need to do that because you never get that high. You never get a solution with that high. At least I don't think so. I guess it'd be highly dangerous. I don't even know how that'd be possible. But if I move down to 10%, that's going to be 0.1. And if I move to 1%, that's 0.01. Do you see what I'm doing here? Now, usually it's nowhere near that high. So you might have 0.1%, which as a decimal looks like that. Remember, percent means divide by 100, so I'm just taking this and dividing by 100. And I can keep doing this. So that'd be 0.0001. All right, now this is getting to more like what we actually see when we do these things. These numbers, and again, these, I'm just doing like the powers of 10, okay, for my percents. It's really not like that. We'll do an example when it's something different, okay? But these numbers right here, they're weird, okay? They go from 1 for 100%, which like I said is probably not going to happen, to these. And each time to go from here to here, it's multiplying by 10, and to go from here to here, you're dividing by 10. So each thing has, the ones I have listed here are off by a magnitude of 10. And even though you put a lot of zeros in here, they look the same, they're really not. So what does that mean? All of these right here, I like to come up with a better scale. So I do this, and it's not me, sorry, I'm putting myself into the story. I'm not the one who came up with this. Check this out. This is where we use a logarithmic scale. So I don't use percents for my calculations, I use decimals. Log is base 10. If I do log of 1, and remember, you already know how to do this. This is actually asking, I don't need a calculator for this. This is asking 10, because this is log base 10, to what power equals 1? That's going to be 0. So if I figure out the log of these, I'm going to get 0. And if I do log of 0.1, or 1/10, again, that's 10 to the negative 1 power. I get negative 1. And you'll see the pattern. Log of 0.01, which is 1/100th, I'm going to get negative 2. Of course, this would be negative 3, that'd be negative 4, etc. So, what chemists prefer is, instead of dealing with these numbers, it's easier just to make it easy like this. All right? However, they still don't like the negative in front of it. So they say, hey, by the way, change all these. So I'm going to put a negative in front of that, which now gives me positive 1. So now my actual scale, my pH scale, is going to be 1, 2, 3, 4, 5, 6, 7. And what happens is that all of these are going to be acids. And of course, anything higher than 7 is actually I don't know if this is the best way of saying it, but it's actually like neutral water. Neutral is the word I was looking for, but I don't know if that's the right thing. But anything higher than this, for like the 8, 9, etc., those become a base, and that means you have the OH, and those are dangerous too. Okay, you don't want to touch them. Okay, so this takes care of like these concentration percentages of how much, and by the way, these percents means like for example, if I had this one right here, that'd be 1% H plus for, and I want to go back to this one. It's the concentration of the hydrogen ions measured depending on like what the solution would be. Usually the solution is water. Okay. Okay, so there's a whole bunch of chemistry here, and I feel really awkward with this because this is stuff that like I studied a lot of chemistry, but I'm bringing up stuff in class that I know that maybe Miss Hanson and Miss Noah would probably just shake their head if they ever see me do this. So here's the math behind it. I want to explain why, and please Google pH. It's actually little p, capital H, like that. Google that, go to Wikipedia, they explain it a lot better than I do, right? So how is this showing up as a problem? Okay, chemists regularly test rain samples, blah, blah, blah. We have an example of the acidity of rain, and we've got, what, 5 different examples here. Here's all that you have to do. Let's go to North Dakota, okay? So this is, and we gotta be careful because remember, how many zeros that you have is the relative concentration of the hydrogen ions, which are protons. H plus is just a proton. So the more you have of that, the more acidic it is. However, the more you have, you're going to have less zeros here, if you think about it, because again, this is a percentage. It's going to be less than 1. So here's what I do, right? I hit the negative sign right here, and you can even save that for last, but that's fine. I hit log, and then I'm going to put this number in. So this is 0.1, 2, 3, 4, 5, 6 zeros, and then 9. So 0.1, 2, 3, 4, 5, 6 zeros, and 9. Close your parentheses. And that is a pH of slightly more than 6. And if you remember from our scale, numbers less than 7 are acidic. The lower the pH number is, the more acidic it is, because it's giving the concentration of hydrogen ions. 7 would be, like I said, neutral water. So it looks like the rain sample that they have here is slightly acidic. 6 is just a little bit less than 7. Okay, let's try Central California. So again, I hit negative log, and this time I've got 0 point, here's the decimal point, 1, 2, 3, 4, 5 zeros, and then 3, 2. 0.1, 2, 3, 4, 5, 3, 2. Now, if I compare those two numbers, I'll try to write them side by side. 0.0000009 and 0.0000032. So lining everything up using the place value, you can tell that 32 is bigger than 9. It's like 3.5 times bigger. So I should expect this to have a lower pH than this one, because the lower the pH, the more acidic it is, and that's true. So instead of 6, now I've got about 5.5. So this is not too hard to do. We'll do the other ones, I don't care, real quick. Negative log, so this is 0, 0, 0, 0, 0.1234629. So in eastern Ohio, that rain has an acidity pH level of 4.2, which is actually getting to be kind of dangerous. New Jersey, got 4 zeros, so negative log 0.0000316. and that's going to give me an acidity of 4.5, and these two would be very close to each other. And then we'll do Eastern Texas down here at the bottom. I've got negative log 0.0000192, and that has a pH of 4.7. And those are relatively pretty acidic. Yeah, so this is one of those examples where I really wish we were spending more time talking about this. And maybe I might try to spend more time in class talking about what's going on here, all right, and giving some background information. But for our purposes, all you'd have to do is just remember it's negative log and then whatever that number is, and then that will give you the pH. All right, we'll see you in the practice problems.